Hello. Today I'm going to do the first of three videos on techniques that are called the local search techniques. They are sometimes also called the advanced search techniques. The first of these is called hill climbing. Each of these is based on an analogy with some other domain, some other part of the world. Now, to do hill climbing, we have to have an arrangement where we have some function that we can minimize or maximize. We have to be able to take each state and compute one function for it. If we want to maximize that function, now think of the function as numbers, and think of it as describing a surface. That function, it describes where we are, the altitude we are in some landscape. If we want to maximize it, what we're trying to do is get to the top of a hill, the largest hill in the landscape. If we're trying to minimize, we're trying to get to the bottom of the deepest pit. Now that's why this is called hill climbing. I know if you do minimize, it should be something else, but they call it hill climbing no matter what. So let's do an example. I picked the 8 puzzle. This is a very standard example for this particular concept. First thing you have to do is define your goal state. But before I do that, I better tell you what the 8 puzzle is. I almost forgot. The 8 puzzle is a grid. And in that, it's 3 by 3. And in that grid, there are 8 tiles. Each tile is numbered. And the tiles can be moved horizontally or vertically, but only into an empty slot. There's one empty slot. And the object is to get the tiles to line up into a particular configuration. If you look at this one here, this is my goal state. And I'm saying I want the first row to be 1, 2, 3, the second to be 4, 5, 6, and the last one to be 7, 8. Now, I could have other goal states, but I'll pick this one. It's one of the more standard ones. Well, the next thing I said is I have to have a function. So what should I do? There are actually many, many different functions. The function I'm choosing is one of the easiest. It's called the Manhattan distance. It's based on the fact that in Manhattan, to go from one place to another, you usually have to go up an avenue, down the street, or left on a street, or it's a grid. And there are diagonals, Broadway, but we don't use them in this definition. What we're doing is saying, when we want to get a tile from one place to another, the only ways we can move are horizontally and vertically. And the Manhattan distance says, look at each tile, determine how many moves it will take to get it to where it should be, and then add those up for all the tiles. Now, of course, when we have it perfectly, we don't have to make any moves. So the goal state's 0. But let's look at this particular start state here and see if we can compute the Manhattan distance. 1 is where it should be. There's no problem there. 3 is not where it should be. It should be where 5 is. So it takes 1 to move it over there. Now, 5 should be in the middle here. So we go down 1 and over 1. That's 2. Our total is 3 so far. 4 is where it should be. 2 has to move up 1. So the 3 we had is now 4. 6 has to move up 1. That's 5. and 7 and 8 are where they should be. So the Manhattan distance of this particular state is 5. What we're going to do is generate the states that we can generate from the state we're at and look at their Manhattan distances. So the 3 states that we can generate, and what I can see, are these 3. We can move we can move the 5 down. We can move the 7 to the right. The 2 to the right, or we can move the 6 up. Now I'm going to try to define the Manhattan distance for each of these. Here I have 1 to get it to there. The 4 is okay. 2 I have 1. That's 2 so far. 5 I have 1. That's 3. 6 I have 1. So that's 4. And I actually have them below here, so let me just, that one's 4. If you look at the other 2, they're both going to turn out to be 5. So if we want to minimize, we take the first choice. So now we look at the children of the first choice. There are only 2 children here. We can move the 5 up or the 3 over. But we've already seen, I think we've seen one of these. I thought we had, but let's see. I think, yes, this one here and this one here are the same. The start state in this one. There's no reason to look at that anymore. I don't want to backtrack. So I'm going to look at this one. Now, does it have a better Manhattan distance? Well, the 3 has to move 1. 2 has to move 1. That's 2. The 5 has to move 1. That's 3. The 6 has to move 1. That's 4. Well, I had 3 there. Pardon me. The 3 doesn't have to move. Pardon me. The 2 has to move 1. The 5 has to move 1. And the 6 has to move 1. So, yeah, it's better. Now, we're going to take that one. So we choose the second one, and we generate its possible children. We can move into that hole. We can move the 2 up. We can move the 1 to the right or the 3 to the left. Now, I think we've seen some of these already. Let me just go down another line. Yeah, we saw the last one. So now we have to compute for the first 2. Well, the only ones out of place are 5 and 6, and they're just 1 away. So that's 2. If we look at the second one, we have to move the 1 over, that's 1, the 2 up, that's 2, the 5 over, that's 3, the 6 up, that's 4. So obviously the first one's better. Now we choose the first one and look at its children. Again, we have 3 choices, and if you compute all of them, you'll find out that the one that has the best Manhattan distance is the third one. So we look at the third one, and one of those children is a go, and we're done. So what we would say is we have to go to this one, that one, the second one up there, and so on to get to there. So that would be the path we would use to get there. But the way to do it, we generate the Manhattan distance and keep minimizing. Now, unfortunately, this is not a perfect method. There are at least 3 problems we have with it. The first problem, what do we do if we have a local maxima or minima? By that I mean we are exploring and we're on top of a hill if we're looking for the maximum, and any way we go is down. It's not better. So do we declare we won and we have the maximum? Well, we could, but we might not have the real maximum. We might be looking at a small foothill when the Rockies are in the distance. So the only one solution to this is that if we get stuck at some place, we randomly choose another place. And we do these enough times, and we always come back to the same place, then we probably have the maximum. If we don't, then we'll keep looking, we'll see which one is best. So the approach again is a solution is to randomly choose another spot to start. Now we can't do that very easily with the 8 puzzle. There are other problems we could do it with. Another way of looking at this is that we're going to send out a team. We're going to parachute a team of people into the landscape, and each of them is going to report back when it gets to a maximum. And whoever has the best, that's the winner. Well, that's one choice. But there's a second problem. What do we do if we get stuck on a plane? Suppose we parachute down, and any way we go is the same. And we take one of those directions, and it's the same. And we keep doing it, and we can't move up. We just seem to be stuck. Well, the solution is the same. Solution is randomly choose somewhere else. Another starting point. There's no other way. Well, that's bad enough, but there's a third one. What do we do if we are on a ridge? Now, this might be a little harder to understand. What we're saying is that we are on a high point, and that high point is the same for a long distance. And the way we've set it up, anywhere we go down. What we might have is something like this. See if I can put the drawer, what I want in. Now I think I'll go here and do it this way. Home. I can't find what I want. Illustration, shapes, that's what I want. We could have something like this. We happen to be right here. So I'll move over to there. Let's say that we are right here. That's us. We're on the ridge, even though you can't quite tell it. Maybe I could just move this line just a little. All right. We're sitting on the ridge. Now, we have set up 4 directions that we're going to look. So we've decided that we can go in this direction, pardon me. Let me try that again. We can go left or right, or Well, first I'll make that stronger. Or we can go up or down, north or south, let's say. So that's what we've decided, that those are the ways that we can run in this particular setup. Now, if you look at that, that means that anywhere we go is down. That's not very straight. Sorry about that. So I'll put it this way. See if I can get down here. Sometimes it's very hard to make the machine move. Okay. We are at X, and we have decided to go north, south, east, or west from where we are. If we do that, we'll never improve. We do not get higher. But the ridge may be going uphill. It's quite possible that this is going better and better. However, if we went northeast along a ridge that is climbing, is going uphill, we could do better. So the solution is, as it usually is, solution is to find a way to go to more neighbors. Now that is the essence of hill climbing. Again, think of it as you have a function, you want to maximize it or increase it. You're thinking of this as the functions form some kind of a landscape. You're dropping down in one place, one state of the problem, and you're going to compute the function there. Then you're going to compute the function of the neighbors or of some of the neighbors. And if you get a better one, you're going to move in that direction. You're going to keep moving until you reach what you want, either a maximum or a minimum, whatever you're looking for. If you find that, that's great. You still can't be certain that you've got the actual maximum though. So if you want to make sure, it might be better to think of dropping several exploratory teams onto the landscape and having each of them do what I just said the one person will do. Now that this is a common technique that is used in many problems. That's going to be it for today. Next time, I'm going to talk about another technique, and I have two more I want to talk about, genetic and simulated annealing. The strangest of them is simulated annealing. It seems to have absolutely nothing to do with what we want, but somehow it works. So we'll take a look at those. I may get this out, the new videos out tomorrow or sometime shortly. I think I'll have them tomorrow. So long now. Thanks.